Good afternoon. Here we are in Chapter 2, Acids and Bases from Wade. And just like every other time, if you have questions about anything in this video, feel free to send me an email and ask about it. We can talk about it via email and answer your questions. But in Chapter 2, it's acids and bases that we're going to be talking about. And acids and bases, you learned about them in Gen Chem. Okay, we'll add on to what you learned in Gen Chem and do it a little bit differently. But the definition of a Bronsted-Lowry acid and base is based on the transfer of a proton. And we all know a proton is a hydrogen atom that's just missing one electron, so it's just an H+. An acid is a proton donor and a base is a proton acceptor. You learned all of that in Gen Chem. One can discuss Bronsted-Lowry acid-base reaction by referring to it as nucleophile. And that's how we'll refer to things throughout the whole semester because it works for all the reactions we can do. So a nucleophile is the same thing as the base. It's something in the name nucleophile or the word nucleophile. It is something that is a nucleus-loving species. And then the electrophile is the same as the acid. It is an electron-loving species. So in this reaction, we're forming a bond between the amide ion going to attack the hydrogen of the methylacetylene, and then the bond between the carbon and the hydrogen is breaking with the electrons going to the carbon. So in this, we form a negative charge on the methylacetylenes. We make the methylacetylide, and our amide ion becomes ammonia because it grabbed a hydrogen off of it. Okay. So in any acid-base reaction, we're going to, if it's a Bronsted-Lowry, we're going to transfer a proton. So, and it'll always be, you'll have to form a bond and break a bond as you're going along. So be careful about that. So here's a listing of the pKa's of some common things. We'll start off Org 1 with just using a few of these, worrying about, we need to know for a carbon, the different hybridizations, an sp3 carbon and sp2 carbon. A nitrogen, we need to know hydrogen gas. We'll kind of use acetylene. That's another hybridization of carbon. And then we'll get into an alcohol, taking a hydrogen off of an oxygen, and then down here to the protonated amines, ammonium salts, and carboxylic acid, and then our strong acids down here at the bottom. Okay, and we'll, as we're going along, we'll work a lot of problems where we mix these in, so don't think you have to memorize them right now. You'll learn these as you work the problems throughout the semester. So in this reaction, and we showed this on the first page, but in all of these reactions, we have the flow of the electron density. Our arrow starts on the nucleophile. It's going to start on the thing that has the most electron density. So in this case, the nitrogen has the negative charge on it. That nitrogen is going to go attack something, and it's going to attack something that has the biggest positive charge on it, the easiest thing to grab, which is going to be a hydrogen, and it'll be the most acidic hydrogen. So a hydrogen on an sp hybridized carbon, like this right here, which we have talked about, has a pKa somewhere in the mid-20s. A sp3 hybridized carbon, and this one would be a little bit different, but an sp3 hybridized carbon has a pKa somewhere around 50. So of those two types of hydrogens, the easiest one to grab is the one on the terminal acetylene. Okay. And that will always be the case in that that's the easiest one to grab between carbons. An sp hybridized carbon is much easier to take a hydrogen off than an sp2. Okay. Now in this, we have to show the arrow for the nitrogen grabbing the hydrogen, and then for the hydrogen-carbon bond breaking with the electrons going to the carbon. We have to show both of those arrows in that mechanism. We can't leave any of that out. Okay? Now in this, we can use the pKa values to predict the position of the equilibrium because we know what happens in an acid-base reaction. In any acid-base reaction, the equilibrium for the reaction always goes to the weaker acid and weaker base. So between these two pKa's, 25 and 36, which one's the weaker acid? The one on the starting material or the one on the product? And we all know that the higher the pKa, the weaker the acid is. So this is the weaker acid, and the methyl acetylide is the weaker base. So the amide ion is the stronger acid, stronger base, excuse me. And the methyl acetylene is the stronger acid in that. So this equilibrium is going to lie towards the products in the reaction. So we can do some calculations about this to figure out how it's going to go. So we can look at a hypothetical reaction with known pKa's and figure out what's going to happen in the reaction. So the first thing in this one, our acid is HZ has a pKa of 5 and acid HA has a pKa of 15. So just from those two things, we know that HZ is the stronger acid of the two and HA is going to be the weaker acid just because of the pKa's of those two. So give the conjugate bases, the difference between the acid and the conjugate base is just going to be the loss of a proton in there. So Z minus is the conjugate base for HZ, and A minus is the conjugate base for HA. Now of those two, the stronger acid would have the weaker conjugate base, because a strong acid has a weak conjugate base, and a weak acid has a stronger conjugate base. So A minus is the stronger base of the two. So what's the reaction going to look like if we take A minus and treat it with HZ? Well, A minus plus HZ, if the reaction were to proceed, we would transfer a proton from HZ to A, so minus, so we'd have HA plus Z minus if the reaction were to proceed as written. So HZ has a pKa of 5, HA has a pKa of 15, so we know HZ is the stronger acid, HA is the weaker acid, so this equilibrium will lie towards products based on just the difference in the pKa of the starting acid and the product acid. So how do we go from the pKa of the both starting acid and product acid and figure out the pKaq? Okay, so we have all these reactions down here. The only one that's equations, the only one that's helpful is the pKaq is equal to the pKa of the starting acid minus the pKa of the product acid. So we can figure out the pKaq for the reaction. So it is 5 for the pKa of the starting acid minus the pKa of the product acid, 15, or a negative 10. Okay, so the pKaq, if it is a negative number, that tells us the reaction goes as written. And the larger the negative number, the more negative it is, the stronger the reaction will go, the more of it will go towards product, the less of an equilibrium there is. Okay, so how can we go from pKaq to KEQ? So we know pKaq is minus the log of the KEQ. So we can take pKeq equal negative log KEQ. Now It's easier to deal with this in log base 10 than natural log, so we won't even go there. So what do we know about this? We know the pKeq is 10, negative 10, is equal to negative the log of KEQ. So we can change the sign on both sides and get a 10 log of KEQ and take the inverse log of that, and we get KEQ equal to 1 times 10 to the 10th. Or the easy way to do it is whatever pKeq is, negative 10 in this example, we change the sign on it and make it the exponent of the 1 times 10 to the whatever. So that's where the 1 times 10 to the 10th ends up coming from. Okay, you can do it the hard way if you want to go through all the calculations, or you can do it that way. Now, what's a change in free energy for the reaction? For this one, we have these reactions up here of delta G, or equations, and the only one that's helpful is the first one, because we don't know what H and delta H and delta S is. We don't need to go into natural log for that one. So the only one that's easy to deal with is the first one, the 2.303 times R times T, times the times the negative log of KEQ, which is equal to the pKeq. So it could be either thing. So if we figure delta G 2.303 times R, which is 1.987 times 10 to the minus 7th, 10 to the minus 3rd, times 298 Kelvin, times a negative 10. Okay, now one thing I would say is the 2.303 times 298 times 1.987 times 10 to the minus 3rd. Those three things are all a constant. They'll never change. So you don't have to do that calculation ever again once you do it once. So delta G is just equal to some constant times the pKeq, which is a negative 10. Okay, that constant, when you multiply these three things out, is 1.36. So delta G is just equal to a negative 13.6 in this case. Okay, so if you remember the 13.6 for that, you can just plug it in to multiply it by whatever pKeq is and get your number. That point gets lost in there, so it's 1.36. Okay, so, or 1.36, 13.6, excuse me. So we can do that with any of these. So think about that as you're going along and use it to help you out. So then down below we have that same reaction we've talked about before. Calculate the delta G for it, KEQ, and the pKeq. So 26, 36. So pKeq is equal to starting acid minus product acid. So negative 10. KEQ is equal to 1 times 10 to the, change the sign on pKeq, make it the exponent, 1 times 10 to the 10th. Delta G is equal to 1.36 times a negative 10, or negative 13.6, just like we did up above. Okay, keep it simple as you're going along. There isn't a lot of calculations in all of this. Okay, so now what factors are there in how acidic something will be? Okay, we have the periodic table. It's hanging in the wall. We have that to help us out. We know that the further to the right the atom is in the same row, the more acidic it is. We know that because HCl is a strong acid. HBr is a strong acid. HI is a strong acid. HF isn't as strong of an acid, but it is more acidic than the others. So the further the right we go, it is more acidic. So a general rule of thumb that I like to talk about in my class to give you some place to start at is, if you think about water, okay, it's a basic solvent, we have it all around us. Okay, the pK for water is basically 16. Okay, 16 is nice in that it's when most people learn to drive, so you can remember it based on that. And if you go either a step to the right or a step to the left from water, it is basically a 20 unit step one way or the other, okay, in pKa. So if we go from water, which has a pK of 16, to ammonia, we're going to get 20 units higher in pK. The pK for ammonia is basically 36, give or take a hair. If we take one more step from ammonia to methane, the pK goes from 36 to basically 50. Okay, so methane, an sp3 hybridized carbon, is the weakest acid that we'll talk about throughout the year. Okay, then when we go from to the right of water, we get more acidic. And we know HCl, HBr, HI, those are the strong acids. 20 units less. It's basically, HCl is basically minus 5, 6, 7, whatever, somewhere right around in there. It doesn't, the exact numbers for these all aren't that important if you know the rough approximation of where they are. Okay, so just going from the periodic table left to right of water, we can come up with those 4 pKa's. And for HCl, HBr, and HI, they're all basically the same. Yes, HI is a little bit stronger acid than HBr, which is a little bit stronger acid than HCl, but not much. So for us, basically a minus 5, 6, or 7 is fine. So then the next thing we can do is can we draw resonance structures for the conjugate base? So if we go from the acid, here we have ethanol and acetic acid. Okay, ethanol is an alcohol, and the alcohol always has a carbon connected to an OH. This is a carboxylic acid. It has a carbonyl with an OH off it, and then that carbonyl is connected to a methyl. Okay, so those two are 2 of the functional groups you need to know by the time the first test comes around, so don't forget those. So when we go from these 2 acids to their conjugate base, all we do is remove a proton from each, so we get the ethoxide and the carboxylate from acetic acid, okay, acetate ion. Of these 2, the ethoxide, we can't draw any resonance structures for that because there's nowhere the electrons can go. They're only on that oxygen. But the acetate ion, we can take one of the lone pairs off of the oxygen, send it down to form a double bond, and take the double bond and send it up to form a lone pair, and we get this resonance structure. So what that tells us is that for acetic acid versus ethanol, we said on the last page ethanol has a pK of 16. Okay, acetic acid has a pK of basically 5. Okay, so it's not as big of a step as going from an oxygen to a nitrogen, 20 units, or an oxygen to a halogen, 20 units. Okay, it's roughly half that because we can now do resonance structures for it. Okay, so being able to draw resonance structures for the conjugate base, we can spread out the charge a little bit, make it more stable. So the more stable it is, the more acidic the conjugate acid is. Okay, so that second is, can we draw resonance structures of the conjugate base? Third thing we want to look at are inductive effects. Okay, here we have acetic acid and here we have trichloroacetic acid. The only difference between the two is the chlorines are very strongly electronegative towards it, so they're pulling electron density away from the carbonyl. So of these two carboxylates, the one with the 3 chlorines on it is pulling electron density very strongly towards the chlorines, away from it. So it's going to stabilize the carboxylate, and that will make acetic acid a little more acidic than, or the trichloroacetic acid a little more acidic than acetic acid. Okay, so this is, I think, has a pK of somewhere around 2 or something like that, versus this one has a pK of basically 5. Okay, so it's even less than the last step of 10. Now we're down to 2 when we change the adding the chlorines on there as an electron withdrawing group near the acid. The fourth thing is what kind of orbital is involved. Here we have an sp3 hybridized carbon, here we have an sp2 hybridized carbon, and here we have an sp hybridized carbon. And of these three, we said already that the sp3 hybridized carbon is the weakest acid, or the strongest conjugate base of the three. We said it had a pK of basically 50 for the sp3 hybridized carbon. The sp2 hybridized carbon is somewhere 38 to 40. For this one, has a pK. Okay, and then the sp is in the mid-20s. To form it, it's the weakest base of these three, just of these three when we're talking about it, or the strongest conjugate acid. So in this molecule, the only hydrogen we would take off if we added a strong base to this would be the hydrogen on the terminal acetylene. That's the only one that's acidic. It's the only one we'd touch. Nothing had happened to the rest of the molecule if we added a strong base to this. So as we're going along, what we need to do is rank the factors that we would look at. You know, the atom, what type of atom is it? Can we draw resonance structures? Is there induction? And do we have orbitals? These four things we will use to answer any of the questions we have to come up with what's going to happen. So here we have a generic reaction down below, and we're going to talk about the equilibrium and how do we tell what the equilibrium is going to be. And we've talked a little bit about this as we've went along, and it basically comes down to, of the two acids, our starting acid and our product acid, which one is the stronger acid? The stronger acid will force the reaction to go away from it, because we always, in an acid-base reaction, we always form the weaker acid and weaker base. You learned in Gen Chem, if you mix hydrochloric acid and sodium hydroxide together, what do? You get salt water. You don't mix salt and water together to get HCl and NaOH. Okay? You always go to the weaker acid and weaker base. So in this reaction, if it were to proceed as written, the base would go grab a hydrogen off of HA to form A minus and HB. The thing with the negative charge is the nucleophile. Okay, the nucleophile, if there is something with a negative charge, it will be on the nucleophile. If you have an acid, it is the electrophile. And we'll talk about this as we get into reactions again as we go on. Okay, so don't think you're only going to see it right here. Okay, so here we have our first example. We have hydroxide and phenol. what's going to happen in the reaction. Which way will the reaction proceed? So first we have the atom, which atom is the charge is on. It's on an oxygen in both. We have hydroxide and we have phenoxide. So it's still an oxygen-hydrogen bond we're talking about. There is no difference in those two, so this won't get us anywhere. Okay? They won't change anything. The OH, just based on it being an OH, should be the same. Now, of the two, the next thing is, can we draw resonance structures for one or the other? The hydroxide, we can't draw any resonance structures for it because all we have are the 3 lone pairs on the oxygen. They can't go anywhere. They're only on that oxygen. But the phenoxide, we can draw resonance structures for it, and you should be able to draw resonance structures for it, where we can send the electrons from the oxygen down into the ring. You should be able to draw 4 resonance structures for it and send the electrons around the ring and back out onto the oxygen. So since we can draw resonance structures for the phenoxide but not the hydroxide, phenoxide is more stable, so it is going to be the weaker base. So that makes phenol the stronger acid and hydroxide the stronger base. So the equilibrium is going to lie towards the products. Okay, and since we've gotten to resonance, we don't have to worry about induction or the orbitals at all. Okay, so right there we know the equilibrium lies to the right. We're done. Now if we knew the pKa's of the two, we could also look at it that way. And the pKa for phenol is somewhere around 10, and the pKa for water is somewhere around 16, give or take a hair. In any reaction, we said the equilibrium goes to the weaker acid and weaker base, so just the pKa's. If we know the pKa's, we know that also goes towards products. So all of that leads towards the products. Here's another reaction we have. Let me change away from the green pen. So we have the cyclohexyl anion and cyclohexanol reacting together to possibly form cyclohexane and the alkoxide from cyclohexanol. So now we start, look at the atom. We have a hydrogen on an oxygen and a hydrogen on a carbon we're talking about. So we have a difference in the atom that the hydrogen is on that we're talking about. And remember from the periodic table, we had carbon, nitrogen, oxygen, and then the halogen, and a hydrogen on an oxygen was 16. When we went this way, we went up 36, 50. When we go to the right, we go down, and somewhere around -5. So a hydrogen on a carbon is 50, a hydrogen on a nitrogen is 36, a hydrogen on an oxygen is 16, and a hydrogen on a chlorine is -5. So of these, hydrogen on oxygen is more acidic, so the cyclohexanol is the strong acid. The cyclohexane is the weak acid. Reaction goes to the weaker acid and weaker base. The reaction goes to the right, just as written. And thinking about the pKa's, we have a pK of 16 for the cyclohexanol and 50 for this. So our pKeq is 16 minus 50, or a -34. So it's very strongly goes towards the product. There is not any equilibrium since that's such a small number. Okay. Now, solvent effects and all, depending on what we have the reaction in, we have to be careful what can happen. So here we have the amide ion and water. Okay, the amide is the ion is the nucleophile because it has the negative charge on it. So if the reaction were to proceed, it would take a hydrogen off water to form ammonia and hydroxide. Now, of this, we have a hydrogen on oxygen versus a hydrogen on nitrogen. We know hydrogen on oxygen has a pK of 16. A hydrogen on nitrogen has a pK of 36. So the equilibrium will lie very strongly to the right. Okay. Now, since we have such a strong base, we can't stick this in water because it would react. If we just put this in water, we do it. We can't add anything else in it. So we need to think about having a solvent instead of water so it doesn't react with the water. So hexane and tetrahydrofuran are two solvents that we can use for this in a reaction so it doesn't get in the way and react with our reagent. Okay, because if we wanted to do something with the amide ion besides reacting with water, it wouldn't happen if we add it to water because it's going to take a hydrogen off of water and not do what we want it to do. So some other things we have to think about are a hydrogen on an oxygen. Ethanol has a pK of 16. T-butanol has 3 more alkyl groups, so it's actually a little weaker of an acid, higher pK than ethanol by 2 units. Okay, for us, for what we talk about, it doesn't matter. They're basically the same. But we'll talk about why this is when we get into chapter 4 in just a minute. Now, in this, we have all the counter ions. We know we can't go to the shelf and grab a bottle NH2 minus because it's got to be neutral. So there has to be a counter ion on it. The counter ion, the sodium, potassium, the lithium, remember what class you're in, organic, sodium, potassium, lithium, they're all useless. They're a means to an end, that they're not something we're going to use the cation as something per se, especially in org 1. So they're just the counter ion. So what we have is Na plus and NH2 minus going on. So we can write it where we ignore the Na plus and just write NH2 minus. We don't have to worry about the sodium. Yes, it's there. We all know it's there, but it's not going to do anything that we need to worry about. So here we have some acids. Give their conjugate base and rank their base from strong to weak. So you need to know what the pKs of different things are. And here's one where we have the base, give the conjugate acid, and rank them from strong to weak. Now, I want you to try on your own before I start writing anything. So I'm going to let the video record for a minute or stop for a minute so that you can try it, and then I'll work it out and see, you can try to see if yours agrees. Okay, so on the first one, conjugate base, all we do is remove the most acidic hydrogen. So we're going to have the acetylide, we're going to have NH2 minus, CH3 minus, On the number 4, we have a hydrogen on an oxygen, a hydrogen on a carbon. We know the hydrogen on the oxygen is more acidic, so we'll have the methoxide. And the last one, we have a hydrogen on an oxygen versus hydrogen on a carbon. So we know it's going to be the hydrogen on the acid, so we're going to get the carboxylate. So we're supposed to rank the conjugate bases. So the only way we can rank the conjugate bases is to know how strong the acids are. So this is a carboxylic acid, number 5. It has a pK of 5. This is an alcohol. It has a pK of basically 16. This is a hydrogen on a nitrogen. It's 36. And then this is a hydrogen on an sp3 hydroxycarbon. It's 50. So the only thing we have to worry about is this one, the top one, the acetylene. What is the pK for it? And we've already said that an acetylene has a pK somewhere around 25, 26. So those are the strengths of the acid. So the strongest acid, the carboxylic acid, is going to have the weakest conjugate base. So to rank bases, this is going to be the weakest. Then from it, methoxide, then the amidion, then the acetylide, and the strongest base is going to be the CH3 minus, okay, or the conjugate base of the weakest acid. So now we go down the bottom one, give the conjugate acid. So all we have to do is put a hydrogen on our base. So it's the ethylene, H2, HNO3, NH4 plus, and CH3CH2OH. So all we do is put a hydrogen on the thing that has a negative charge. And yes, on this one, the negative charge is a little hard to see. They're small, I know. So the only one that doesn't have a negative charge is the ammonia. So the ammonium ends up with a +1 charge. So now we rank the acids from strongest acid to weakest acid. Now of these, we know this, the middle one, nitric acid, is an acid, so it's obviously going to be number 1. Then, so it has a pK somewhere around -1. Ammonium is about 9, ethanol 16, and these two are pretty close to the same, 36 to 40, okay, H2 and the ethylene. So it's really, those two really aren't a good choice for the problem. So the nitric acid is 1, the ammonium is 2, the ethanol is 3, and then of the other two, 4 and 5. Okay, so on to the next page. So here we have, let me get rid of that. We have a reaction drawn here. It's a Lewis acid-base reaction, and in a Lewis acid-base reaction, we have the movement of the electrons. We have the electron donor, which is the nucleophile, and the electron acceptor, which is the electrophile. And Lewis acid-base reaction is kind of what we'll do a lot of throughout the semester. So in this, we have the nitrogen to show the arrows. The nitrogen is the nucleophile. It's the thing that wants a nucleus. It goes and attacks the carbon, kicking out the chlorine, giving us the two products there. Okay, and you should be able to draw in all of these the arrows for the transfer of electrons, because what we see in the reaction, the chlorine goes from neutral to negatively charged, so it gained 2 electrons. The nitrogen went from having a lone pair to having 4 bonds, so it lost 2 electrons assigned to just it. So as you're going along, be careful how you draw the mechanisms, how you draw the arrows. The arrows are very important as we show things. So here we have some example reactions to draw through what will be the type of question that will be asked on the test. So in the first part, we have where it asks us to predict the products for the following acid-base reaction. It is a Bronsted-Lowry acid-base reaction, so we're going to just take a hydrogen off of the acid, the thing with the positive charge, and put it on the thing with the negative. So we're going to form water along with trimethylamine. Okay. Oops, no circle on that one, just a plus. So we're going to form those two things. Now the mechanism for this would be the OH grabbing the hydrogen off of the ammonium, sending the electrons to the hydrogen. Now in the next one, and we knew the OH was the nucleophile and the ammonium was the electrophile because they each had a charge. The hydroxide had a negative charge, the ammonium salt had a positive charge. A negative charge means nucleophile, positive charge means electrophile. Okay, now in the next one, ammonia and water, they're both neutral, so we can't look at just the charge and see which one's going to be the nucleophile. We have to look at the pKa's of things, and we know the pKa of water is 16 and the pKa for ammonia is 20 units higher, 36. So of the two of them, water is the stronger acid, so the ammonia is going to grab a hydrogen off of the water and it's going to form hydroxide along with the ammonium salt if the reaction proceeds as written. In the next one, we have the NH2 minus. It's going to be the nucleophile. The water will be the electrophile. So the NH2 minus is going to grab a hydrogen off of the water. We're going to form hydroxide again along with NH3. Okay. Now these don't ask us to predict where the equilibrium lies. It's just draw the mechanism and predict the product for the reaction. So on the next one, we have the same sort of thing. Complete the following reactions. It doesn't say draw the mechanism, but we will show that. So this has it's too small of a dot, pardon me. We have the nucleophile and the electrophile. So because this has a negative charge on it, so this CH2 minus is going to grab a hydrogen and become CH3, and it's going to take a hydrogen off of the acetylene to form the acetylide. So the mechanism would just be something like that. Well, let's draw it out. So it's going to be where we have CH3, CH2 minus plus and it's going to go grab a hydrogen off of the carbon to form the product. Okay, so now we have this ethane. Ethane's going to bubble out of solution. It's a gas, so it's gone when we look at the solution from A, and we're going to add the acetylide ion, and we know that acetylide, the negative charge, is a strong base. It's going to grab a hydrogen off of D2O, deuterium off of D2O. We know what DOD is. We learned in Gen Chem. D is deuterium. It's an isotope of hydrogen. We all know that. So all we're going to do is put the deuterium on there and then have OD minus left over. Now, if you have an isotope of hydrogen, you need to write it as showing that it is the isotope. You cannot put an H there and leave it. If you draw an H, you have to put the superscript of the 2 to show that it is a deuterium, that it weighs 2. Okay, if you just put an H, that's a regular H, that makes it wrong. So that's that one. The next one, we have the hydride and ethanol. So we're going to take a hydrogen off of the ethanol and form H2 along with the CH3, CH2O minus, because we take a hydrogen off. Remember, the hydride is the nucleophile, the ethanol is the electrophile. In this, it's going to take off the most acidic hydrogen, the hydrogen that's easiest to take off, which is the hydrogen on the oxygen, so we could draw it out. The hydride grabs the hydrogen and we kick it off. Okay, nothing to it. That gives us hydrogen gas. In the next one, we have HI. HI is a strong acid, so it is the electrophile, and we have ethanol. It's going to be the nucleophile. So the nucleophile is going to go grab a hydrogen off of HI, sending the electrons to the I, give us I minus along with CH3, CH2, OH2 plus. Because all we did was take the I off of the, or the H off of the I minus, HI. Okay, and the last one here, since we've had this bottom part to look at, I'm going to erase it so we have a little space to write. But we have this H2CC, and we all know that has to be drawn this way, where the carbons have a double bond between them. And H2SO4 we know is sulfuric acid, HSOH, 2 single bonds, 2 double bonds. Better draw a bond to the H so we have something to break off. So all that's going to happen in this is the double bond's going to go grab the hydrogen off of the sulfuric acid. So we're going to have the bisulfate ion with 1 negative charge, and then we put a hydrogen on one of the carbons of this, so we're going to have a CH3 bonded to a CH2. We put an H plus on it, so overall it has to have a plus charge on it. Overall, the ethylene and the sulfuric acid were neutral that we started with, so in the end they have to end up summing to neutral. Since we had the bisulfate negative charge, we have to have something with a positive charge to balance it out. Okay, and then we have this page here of some more reactions very similar to the last ones. Draw the curved arrow mechanisms. So in this, we kind of need to show the bond we're breaking. So draw in ammonia, the carbon with a negative charge grabs a hydrogen off of the ammonia, and we get the NH2 minus and the ethane. Then we have the ammonium ion, 4 hydrogens on it with a positive charge on the nitrogen. The oxygen grab a hydrogen, send the electrons to the nitrogen. We know this C6H5COH is a carboxylic acid. So we draw out a carboxylic acid, take the H off, and we have that. Negative charge grabs a hydrogen, takes the electrons off, giving us the acetylide ion. Now the acetylide ion takes the deuterium off of DOD to give us the deuterated acetylene. And then the last one, the pi bond, is going to go grab a hydrogen off of HI to give us the protonated carbon. And then the I minus adds in to form our product. Okay, now this is something that in class, probably not tomorrow or not Thursday, the second day of class, probably next week, Tuesday, there will be a handout on this that you guys will try. You won't have this in front of you, but to try to get you to work through this type of thing. When you have to draw a mechanism, draw out the molecule you have to show the bond you have to break off. Okay, like I did up here at the top of this page. Don't just put it on there and take something off from the, if it's drawn this way, it's hard to see what you're doing as you're going to go study that. Okay, draw it out with the bonds to hydrogen. You can throw the lone pair in if you want to, you don't have to. Okay, but then your nucleophile, whatever it is, can grab a hydrogen, and you can see on the page in your notes as you're studying later on what's happening with it. Okay. Okay, one more page of this chapter and we're done. Here's our functional groups. We all know an alkane, and this says draw a small molecule as an example. So a small molecule for an alkane could just be ethane. An alkane is just an sp3 hybridized carbon. An alkene has a double bond in it. An alkyne has a triple bond in it. An alkyl halide, since it just says a halide, it's your choice, fluoride, chloride, bromide, iodide, whatever. So it could just be a methyl chloride, and that would be fine. If it said an alkyl iodide on the test, make sure you would draw methyl iodide. Okay, be careful what you draw, that it answers the question. An aromatic ring is just a 6-membered ring with the 3 double bonds alternating. A nitrile is a CN triple bond. We won't use it much till we get later on, so don't worry too much about it. An ether is an oxygen with 2 alkyl groups on either side. Okay, and the ether and the ester are hard to keep track of, so be careful. Look, make some note cards of them, flip them over, and work on what are the functional groups. An ester is more complicated than an ether. It has the carbonyl in there also. Okay, and then the amide, instead of the single bonded oxygen of the ester, we'll make it an easy amide. We just have a nitrogen in place of the oxygen in there. Okay, and then an aldehyde is a carbonyl with a hydrogen on one side and a carbon on one side. A ketone, and notice the spelling of ketone. It does not have a Y in it. It's not that type of key. A ketone has alkyl groups on either side, and an alkyl group, methyl, ethyl, propyl, it doesn't matter. If you're answering a question like this, keep it a methyl. Make it as small as possible. It doesn't have to be fancy in what you draw. A carboxylic acid is another one that has a carbonyl, and then off of that carbonyl it has an OH. So it's slightly easier than the ester because it has the hydrogen on the oxygen, single bonded oxygen, instead of the carbon there. A primary amine, an amine in general, is a nitrogen. Okay, so a primary amine has a nitrogen with 1 alkyl group on it and 2 hydrogens. A secondary amine is a nitrogen with 1 hydrogen and 2 alkyl groups, and a tertiary amine has 3 alkyl groups. And that's the only 3 possibilities you can have for an amine, a primary, secondary, or tertiary amine. And it's just how many alkyl groups are on that nitrogen. And then an alcohol, in itself, an alcohol is a carbon connected to an OH. So primary, secondary, and tertiary alcohols are slightly different than the amines. The amine, you're talking about how many carbons are on the nitrogen, because the nitrogen can have more than 2 things to it. Okay, so but with an alcohol, a primary alcohol has 1 carbon on the carbon containing the alcohol and 2 hydrogens. A secondary has 2 carbons and a hydrogen, and a tertiary has 3 carbons on it. Okay, so these are your functional groups. You need to know these by the time the test rolls around. If you don't, there's 10 points you're going to lose, and we don't want that to happen. Okay, so this is the end of chapter 2, and so I'll make the video for this one and then upload it, and then I'll do chapter 3 later. Have a good day. Send me any questions you have via email. Thanks.